Okay, so this is our CEE 11 final project on Huntington Beach TC data, and we are group 12. So first off, just a little background on why we want to study TC. So even though the concentration of TC in the water has been decreasing over the past 40 years, our biggest concern is spikes in TC that we have, on a more short-term basis. And these occur near outlets like the Santa Ana River outlet where it leads into the ocean. These happen to be in highly populated areas like Huntington Beach. So it's not, the kind of low-level averages that we have for a long period of time. So big spikes that get people sick. We want to learn why those happen and how to kind of control those. So what we're going to discuss is we're going to prepare some CDFs from the data given, and we're going to put some analytical distributions on those 3 station CDFs and find the parameters. And then we're going to do something similar for salinity and temperature, have some analytical distributions for them, and then just look at the extreme values and how those kind of correlate and come up with hypotheses based on those. So part 1 was just organizing data and plotting the CDFs. So our group was given data from 1991 to 1994. And, there was some sensor data in this 3-year period. It only went down to about 20 TC and up to 160,000. So we could have values above and below that. And then also in between, there were some days that just didn't have data for them. So that was censored and was not really applied to our project. So first off, just kind of making the CDFs for each station. So we did the log normal CDFs just to make our data look a little bit prettier. So basically that's just finding the concentration of CDF, concentration of TC and how many times that occurs relative to the total number of data points that we have. So as you can see, this is our north graph from station CDF. Here's the south, and here's the 0 station CDF. So we wanted to plot all of them together so that we can make a comparison and a statement about what this means for the concentration in particular areas. So how we do this is we want to take a single concentration. So our sample calculation was to pick a concentration of 3.8. This is the LN, RTC, so 3.8 right here. And we want to figure out what the probability is at that point. So on the y-axis, we have the probability of the concentration being less than 3.8. So for the Santa Ana River outlet, the probability is about 0.6 or 60% that the concentration is less than TC. And if you look for the south, and is a little bit higher, and the north is actually the highest. So to find out the actual probability of it being greater, we want to take 1 minus whatever probability we had. So what this says for the north, or the 0 station, is there's a 1 minus 60, so a 40% chance of finding greater TC concentrations. But if you look at the north station, it's about 1 minus 0.8, so 20% chance of finding greater TC concentrations. So you have a lower chance of finding higher TC concentrations at the north station, so that's the one you'd want to recreate. So next is part 2, and I'm going to hand that over to Darren.
All right, thank you, Austin. So for part 2, we're finding parameters and fitting a curve to the CDF. And this slide just shows the basic tools and equations we use to find parameters. All right, so in order to solve for the parameters, we have to calculate lambda and zeta by picking 2 points on the CDF. For example, we pick these 2 points and set them equal to each other by using the log normal distribution equations, which are these. So after manually calculating the parameters, we've come to the conclusion that the north normal CDF, we ended up with the parameters lambda being 2.9 and zeta being 2.5. And now what we do after that is we plug these parameters into the error function, which we then put into MATLAB to give us a plot of the best fit curve. And we compare this best fit curve to the empirical CDF for each one of the graphs. So for instance, here we have it for the south normal distribution. We found its parameters, plugged it in, and there you go. And same with the 0 or Santa Ana CDF for log or ln transform with TC. So what does this mean? In conclusion, we created these best fit lines because the best fit CDF lines provide a better representation of the actual probability of the empirical CDF. And that will help us better decide on which stations is the best station to recreate at. In addition to just best fitting the lines, we also did a mean comparison test to figure out which station would be the best one to recreate at. So how we found the mean variance and how we found these two variables is that we used the equations provided in the online lectures, and then we plug that into our MATLAB code. And you can check our MATLAB code if you want to see how we solve for these values. But if you look closely, you see that the mean of the TC for the north is a lot lower than the TC at the Santa Ana station or at the south stations. So this implies already, just by finding the mean and comparing them, that there's less TC concentration at the north stations. All right, so after that, what we did, we took those variables and then we created the T statistic. So what the T statistic reveals is whether the two samples are from two samples from two different stations are drawn from the same population. So what that means is that we basically just compare the means and see if they're like reasonably close to each other, that we can say that they're somewhat related. Like for instance, if you look at the concentration of, or the mean concentration of north compared to 0, you'd see that they're way off. Same with south and 0. And that's seen in this right here graph. And how we determine tolerance is that we picked 0.05 tolerance. And what we did was we divided that in 2 because this is a two-sided distribution. And the points that go beyond this limit right here, negative 1.96 and 1.96, are the points where we reject the null hypothesis, and the points that lie between these two are where is where we reject the alternative hypothesis. So what is okay? So basically, what that means is that at this point, it's reasonable. The north and south means are very reasonably close to each other. That's why we accept it. And for these, they're nowhere near each other, so we do not. So okay. So follow-up questions. When comparing parts 1 and 2, the data was by no means a perfect match, but the values we got in part 2 are consistent with the more qualitative results in part 1. Based on our analytical approach in part 2, we supported the assumption that north stations still seem to be the safest to recreate since there's lower probability in finding TC concentrations. And now for part 3, I'm going to hand it over to Austin.
All right, thank you. So this is finding and fitting the CDFs of salinity and temperature. So this part is very similar to what we did in step 1, where we made some CDFs, except these are for temperature and salinity. So right here we have our temperature CDF graph, and then also we had some other analytical graphs on here, just to kind of find a best fit that would match our CDF. So if you look, our log normal ended up being the best fit, and that is the red line right here. It's actually pretty close to the normal distribution as well. And then how we arrived at that conclusion, this right here is our MATLAB code to come up with the actual analytical graphs that we have on there. These are our adjusted R2 values. So we took one for each analytical solution, and the closer that these values were to 1, the closer they were to actually matching our CDF that we had. So as you can see, the log normal adjusted R2 for this value was the closest to 1. It was 0.9873, so it was the best fit. And similarly with the salinity graph, we had our original salinity CDF, and we had some different analytical graphs on here. The best fit was the beta distribution. That's the blue line right here. And if you look, MATLAB code to graph those, and then our adjusted R2 values, the closest to 1 being beta, and that was 0.8277. So next on to part 4, which was finding correlation between the data and forming a hypothesis test. So the first step in doing that was to actually come up with the exact distribution. So essentially what we're doing here is we want to pick an n value. So just n is the number of samples that we're taking. Then we have a number of iterations that we want to run it through in our MATLAB code. So based off our parameters, this is for the 0 station right here. We have our lambda and our zeta. that we derived earlier in our calculations, and we plugged in MATLAB code to come up with these exact distributions. So we picked different n values. The first one was n equals 5, the second one being n equals to 100. And we have our empirical CDF data, which is this red line, and you have the nice, smooth, exact CDF. And if you look over the 100 value, the big difference between having a higher n value is what we notice that they tend to concentrate more towards one number. So this trends like between 8 and 10. Here it spreads out a little bit more. If you look at the extremes, where n is equal to 1, you actually get just our regular CDF that we had from part 1. And then you have the exact CDF to kind of follow along it. And if you do the max, so our max concentration that we found was n being 738, everything concentrated this one value here, so it's just straight up and down. So that's what we tended to notice with our data.
All right. Continuing on the topic of correlations, what we did next was we found the conditional probability. And when we do conditional probability, we first find the extreme values, and how we consider that is we look at the top or bottom 15% of the sample data as extremes. So in this case, we chose TC being greater than 1,000, conditioned on the temperature being greater than 15 and salinity being greater than 31. Okay, in order to solve for these conditional probability, we use the equations below, which are found on the online lecture notes. So here, this is the equation used to find conditional probability, and this one's used to find variance. And we wrote a MATLAB script solving for all of these. So if you guys want to see all the calculations, feel free to look it up on our MATLAB scripts. Okay, so in this slide, it actually shows all the conditional probabilities for both temperature and salinity. And what you're going to see in the next slide is that these numbers actually support our hypothesis of why, or our initial assumption of why recreating at the north would be the safest option between all the stations. All right, so here what we did was we graphed our calculations to find on a conditional probability graph. So right here, you'd see this is the conditional probability of temperature. And here you'd see that at this point, it's really low because at this point, one represents north 15 and 9 represents south 15, with 5 being the 0 station or the Santa Ana River. So like we said, the north station would, based on the earlier empirical CDFs, would have lower probability of TC concentrations, and this right here just helps us prove that some more by looking at the data. If you add all these up, it'd still be less than the conditional probability at station 0, and the same at south. It would be less than 0, but it would be greater than the northern stations. And the same goes for the probability of salinity. Okay. So basically, these graphs just help us. What do you call it? Further validate our earlier assumption. So now that we got the conditional probabilities, what we want to do now is we're testing for proportions. So what this means is that this right here, hypothesis, is going to tell us whether our proportions are from the same population or not. Okay, so how we do that is first we set a hypothesis, a null hypothesis, and a alternate hypothesis, and we solve for them using these. And how we do that is we have to find the z-score and the probability, or p-hat, sorry. And we use MATLAB again to solve and calculate these values, so feel free to look that up again. Okay, and in this test, we use the 5% error, which is distributed between the two tails. So we have a 2.5 error tolerance on each tail. That's why we get this number, if you look at the chart. Okay, so this is the hypothesis testing for temperature. Right here are the z-scores for it, and here are the stations. As you can see, all of the z-scores are within the tolerance. So what we're going to do is we're going to reject the alternative hypothesis for temperature. And then, so for this is now testing for salinity, and you can see all the z-scores are also within the tolerance for all stations. So basically what this means is that they're all from the same population. And I'll further elaborate on that on the next slide. Okay, so here, our testing results after solving for the hypothesis, we came to the conclusion of rejecting the alternative hypothesis. The alternative hypothesis basically states that the proportions are different from each other. By rejecting the alternative, we concluded that two proportions are drawn from the same population, and being from the same population implies that there are no outside elements found on the other stations that could possibly affect the probability of TC being greater than 1,000. So all in all, the comparison of proportions and hypothesis testing further validates our initial assumption on recreating on North Station, because that just means that no other variable is going to change the TC concentration on the South or the Zero Station, because they're all drawn from the same population. So in conclusion, overall, we have decided that the best place to recreate is at the North Stations because they contain the least amount of TC as seen in the empirical CDF graphs. However, that wasn't enough to fully support our claim. Therefore, we supported our initial hypothesis of recreating at the North Stations by doing a mean comparison test. A mean comparison of a mean comparison of proportion test and a hypothesis testing. According to our mean comparison test, we realized that the TC mean of the North Stations are a lot lower than the other ones found in the other stations. Moreover, to further support our hypothesis, we tested the extreme values of TC conditioned on temperature and salinity using conditional probability. Once we got the conditional probabilities, we then used those values to determine whether temperature salinity will affect TC being greater than 1,000. And it turns out that since our conditional probabilities were so low, that temperature and salinity did not really affect TC being greater than 1,000. So after solving for the hypothesis, came to the conclusion that the samples were taken from the same population, meaning that temperature 15 or salinity being greater than 31 does not affect TC being greater than 1,000. However, we need to further testing to determine whether temperature being less than 15 or salinity less than 31 will actually affect TC being greater than 1,000. And to end it all, so here's our speculation on why we think that the TC is all distributed that way. Since TC is more concentrated, or TC concentration can be found more in the Zero Station or the Santa Ana River, we conclude that TC originates from sewage runoff carried by the Santa Ana River to Huntington Beach.
So that was the end of our project. Thank you very much. And yeah, thank you.